quantum Fourier transform, so QFT. This is what we so this is where we left last time, and what I'm trying to do today is I'm going to try to explore a bit more the actual problem, because I think in the last video we just jumped into building the solution that was proposed here, without really understanding was. I have the impression I didn't have good understanding of the problem. So I want to just back up a little bit, and then just to remind you, this is an example where we're preparing an input that we know is going to give us a 001 as an answer, and this is the actual. So this is actually step number 1, step number 2, step number 3. So it's like this is the actual way you build a QFT. But I have the suspicion that, as in most of the cases in quantum algorithms, is that they exploit the structure of your initial state. So the reason these steps work is because we know that this has been prepared in a way that we can exploit certain properties of the state. Might be positive and negative uncertainty, might be that the phases or that things are set up in a certain way. I don't know, but I think that's what. So I want to understand. I don't really like the way this is presented here. I don't really like the fact that this is so that the example given is just they just prepare something which obviously has some rotations here, which they are they're thought in hindsight, right? Because those are exactly the same rotations we're making here. So I understand that for the sake of the example, it's good, but it's yeah. So basically, I've done two things. I've opened up this morning. Basically, I've done a bit of googling around, and I also started taking a look at this blog, which is written by Craig Gibney, which is basically this blog was shared. I was not aware of the existence of this. One of my subscribers of the channel shared that with me, and I think that it's a really I haven't really gone through all that at all. Just read a little bit at the beginning, but I saw that there is a topic about how do we prepare the states. I think that it's definitely worth taking a look at, because also I again ended up back at David's Kopchik blog, where basically explains a bit the same thing, and at least the problem is a bit clearer, because here he explains it in a way that, so we've got a function, we've got a wave, right? And so oh, wait a second, this was not here. I think this was where did I find that? Where did I find that? I was reading something this morning. No, efficiently. That's not what I'm looking for. Quantum discrete Fourier transform. The other way around. Let's just discrete Fourier transform. I just found something this morning which was really eye-opening in terms of understanding the problem. Maybe this one. Yeah. This is it. I mean, because basically I understood thanks to that what DFT really is, right? So the idea is, imagine you've got, and I was really not far away from that, but I couldn't really grasp what was the D, or like the why was it discrete or whatever. So imagine you have that wave, right? So what you want to do at the end of the day is you want to know how, like, what are the components that make up to these. So this is definitely not a sort of maybe we can call it a pure wave, or it's sort of like it has its own weird shape. So it's obviously the result of composing two or more waves. So you want to find what are the periods, I think, of those functions that make up for this one. But the way you do that is first you sample. So first, and that's why it's called discrete, I guess. So first you take your, because that's sort of like a continuous function. And first what you do is you based on a period, right, t, you sample with equally spaced, I think. And that's kind of also what we're going to use in the quantum. I have the impression this is one of the reasons why the quantum algorithm is designed the way it is. But let's go step by step. So this is, we basically sample those points, right? And that's our input vector. So that's our input. So this is the input of the problem. So you've got that sample. You don't have the full thing. You've got that sample, and out of that sample, you wanna basically have a I don't know what you want to have, but basically what you want to have. Samples, equations. You want to have, I think here David explains it well. So what you want to have is frequency filters, blah blah blah. So so the frequencies is what you want to have. Okay, so we want to have basically the frequencies of the waves that make up for that input. Exactly. So before we, what is the Fourier transform? So you've got a vector and it maps into a new vector. So this is our input that I just checked in here, right? So this is your sampling of that. And then we want to turn it into this, and that's it seems almost one-to-one to what the IBM guys. To understand it, assume input signal consists of a true signal with frequency f10 and amplitude 2. So it's described by this equation. And a noise. Okay, so here's an example of a true signal. That's exactly what I meant in the sense that, okay, so this is explaining. Imagine that this is your input here, right? So this is your input. So imagine we know a priori that's made up of those two things, of this and then a little bit of noise, and this plus this kind of make this signal, right? So and why this is useful, I guess one of the applications is if you're able to get this and this out of just analyzing that, then you can cancel the noise and do other stuff like that, right? So that's kind of, I guess, how a lot of the stuff works now with noise canceling or sort of basically signal processing, whatever. So I guess what you want to have. Okay, so that's the output you want to have. Is it correct? After DFT. So you want to have two frequencies. Is it correct? One frequency is 10, amplitude 2. I know the amplitudes. Okay, look at this. Amplitude 2 and amplitude 0.3. And this is what you have here. So here you've got 0.3 and here you've got 2. So that's what you want to get out. And those are the frequencies. Okay, so this is so here you've got, so here we've got the amplitude, and here we've got the frequencies. So you've got frequency 10 and frequency 50. Exactly. I don't understand all those dots. So that's what we want, and that makes the approaching the problem much more understandable. So we basically want to we want to get and how this is going to be useful for Shor's algorithm, I don't know, but we will see, right? And I think this is apparently useful for other algorithms as well. So we want to basically get that. So we have this input signal, and we want to understand which frequencies this is made up of. Now, I wanted to, for this video, I wanted to understand how can we represent that how can we represent the inputs and the outputs? Like, what's the concept in the quantum version of it, because I think that's going to help me. So my idea is that this is going to help me understand the actual algorithm. So this video, we're going to focus on understanding how the inputs are encoded, and then that hopefully will make it easy to understand the algorithm. So, and I'm gonna I think here. So here basically I'm gonna skip the first part where they basically it is so they explain basically the Shor's factoring algorithm, sort of the overview. I haven't really gone through this. And a bit of background on the Fourier transform, and then I guess the signals and signal processing and stuff like that. But I think this is where it's interesting, probably. So if you have a computer, possible 32 states you can be in. There is da, 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 da. So the thing that separates a quantum computer from a classical computer is that a quantum computer can rotate its state through particular weighted combinations of the classical states, called superpositions. Exactly. Okay, so you can write down possible states of qubits. This we know, all this stuff. So yeah, so you have 5 qubits, and you can basically write some things like like this here, right? Or like this here, or like this here. So a lot of fun combinations. In this pause, when I say periodic state, I mean a superposition where the weights of the classical states go like 0, 0, 0, 0, not 0, 0, 0, 0, 0, not 0. Okay. So it seems like because I'm guessing and I'm making a big guess when he talks about periodic states, this is about encoding the input, because at the end of the day, here and also here, that's what it happens, right? So this is our input and this is the period, right? 1 period, 2 periods, 3 periods, 4 periods. So we want to encode those things. Okay, I understand. So the way that he's suggesting to encode that is by saying that, so we're gonna have a superposition where the amplitudes are going to be the ones encoding the actual samples, right? So let's say this is 0.25 and this is like 0.75, right? So, but they're going to be equally spaced by states where they'll have 0 probability. Okay, 0, 0. So 4 zeros and then 1 amplitude, 4 zeros and 1 amplitude, and so forth. In other words, the classical states that have non-zero weights should be evenly spaced. And I bet you that this evenly spaced is going to probably play a good trick into understanding how the algorithm works. It's just my intuition is telling me that, but and they should all have their non-zero weight. Okay, the same. So wait a second. So I'm not completely right. I thought that this was the value you were encoding, but that would not make sense. Okay. For example. Okay, so we've got an example. So here we've got an example. So if you've got the state 0, the state 5, or here have 0, 5, 10, 15, 20, 25, and 30 is a periodic state. It gives 1 divided by the square root of 7 weight to the states 0, blah, blah, blah. And all the other ones aren't given any weight. So you see there's a difference of 5 in between. In decimal, okay, so it's a periodic state with period 5. Okay. Okay, yeah. A more compact way to write the state is with summation notation. Okay, but we don't care about this right now. At this point, a certain subset of readers are probably thinking something along the lines superposition, but I bet the quantum computer is just secretly in one of those states. Okay, let me just remove this. Yeah, superpositions are real. So the specific quantum operation we care about in this post is the QFT. What the QFT does, it's like it takes the weights of the states, pretends they are the samples making up an audio file. Yeah, but they are all equal. And your samples won't be equal. figures out what the frequencies in that audio are, then uses the strength of each frequency. So maybe that's just the first step, and then we're going to tweak the amplitudes to actually make them become the samples. But that would be weird because the amplitudes might always sum up to one, sort of the probabilities. Figures out what the frequencies in the audio are, and uses the strength of each frequency as the new weights defining the state of the computer. A good predictor for whether you even slightly understood that last sentence is whether or not your mind just got blown hard. It's all the time being blown hard, man. If you start with the classical state and apply QFT, the resulting frequency spectrum looks completely flat. The classical state. Okay. All the action is in the phases, not in the magnitudes. By contrast, the frequency spectrum of a periodic signal is definitely not flat. Like the spectrograms from earlier, the frequency spectrums of blah blah blah. If the quantum computer was really in just one of the classical states, how could a property about the spacing between the possible states be getting into the output? Exactly. So you see, the spacing is crucial here. The frequency spectrum tells a very clear story about what's really going on. Concrete example. The green rectangle on the left is a chance display. It's showing for each classical state the probability that measuring the superposition at that point would return that state. Okay, so that's exactly what we've done. So it's separated by 1, 2, 3, 4, 5, 6. It's a bit more. I don't know. It's probably not the same example. Definitely not, because we use 5 qubits. Here's more. For the purpose of this post, all that matters is that it can be done. Okay, so I'm happy that he's ignoring the QFT for the moment. We're caring about the inputs and the outputs first, so we understand how the algorithm is built. The rectangle on the right is a chance display of showing the probabilities of getting various outcomes when measuring the output state. It has 10 evenly spaced peaks. Why 10? Because the number of frequency peaks is behaving just like it did with the periodic. The input state's period is 10. So the frequency space output has 10 peaks. Okay. Just to check that. If the output has a number of peaks equal to the period of the input. Okay. Before we continue, I want to address why we're bothering with frequency space at all. If we are rather the period of the signal, after the period of the signal, why not just get it by looking directly at the input signal? Keep in mind that the green displays and diagrams are not available in real life. Yeah, sure. Still, why don't we just sample the initial signals several times and watch for patterns? Why can't we figure out the period by sampling the input signal? Gee, there sure are a lot of multiples of 5 in here. The problem with noticing that a certain multiple keeps happening again and again is that, as you'll see later in the problem we care about, the signal we're sampling from is going to have a random offset. If we sample the number 213, that could be 50 times 4, or 13 times, or 13, or 10 times 21, with an offset of 3. Okay, let's just go. Another thing you should notice above diagram is that the frequency peaks are resilient to little imperfections. Preparing a periodic quantum state. I've explained that, that's probably the interesting part. I've explained that if we had a periodic quantum state with unknown period, we could sample from the peaks in frequency space in order to learn something about the period. But how do we prepare that periodic state in the first place? First, in an easy case, if the period we want is a power of 2, let's say 2 to the power of 3, then preparing a periodic state is simple. Start with an n qubit quantum register initialized to 0, do nothing to the first 3 qubits, and hit the rest of the qubits with the Hadamard gate. Each qubit you hit with the Hadamard gate will transition from 0 to this superposition, putting the overall quantum register into the state. Bam. That is a periodic state with period 2, 3. Really? Let's so an n qubit. But can I pick the ni1? If I'm just going to start a new one. I would like to stick to the example of 3 because it makes visualization easier. So if I do this, so there's an, if I do that, yeah, okay. Yeah, of course, because you're leaving that 0 untouched here. Exactly. So those are, and now we have here, so you see this, like there's 1 in between each, right? Or in this case, there's 3 in between each. Okay. Not sure entirely how this is gonna. So an alternative way to create a quantum state that has period 8 is to hit every qubit with a Hadamard gate at the register we want to prepare into a register of size 3. Then measure the other register and try again if the result isn't 0. Okay. Pretty crazy. Preparing other periodic states. Instead of doing a 3-bit addition, like model 8, we can do addition modulus some other number. Okay. For example, here's the proposed periodic quantum state with period 7. Then applies a Fourier transform to show that there are 7 peaks in the output state. Okay, I'm gonna skip that for the moment. I think we can dive into this later on in another video on how to prepare those states, but I want to go a little bit farther without getting into the depth here. We got a simple example where we prepare. Let's do it like this. So we prepare that with period 1. Okay. 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 Those are other ways to prepare other types of preparing other periodic states, figuring out periods from frequency samples. But I think that's already the other part of the QFT that I wanted to avoid getting into before understanding. No, or wait a second, we're still in QFT, right? We're still figuring out periods from frequency samples. Here's a bit of a puzzle for you. I'm going to show a circuit that prepares a periodic state using modulo addition like the last sections, but I'm going to hide which modulus I'm using. Your job is to figure out the secret modulus. 3 peaks, so the R is 3. But remember, when running an actual computation, less than 6. Preparing states with unknown periods. Turning a period into an extra square root, putting it all together. Okay, but I didn't want to go all the way through the entire Schur's algorithm. I wanted to understand why. So the problem is that I feel it feels. I think this article, there could be an interesting view on the Schur's algorithm, but it kind of goes all the way through. I really wanted to understand how QFT, why QFT works, and how does it work, really. Um, so what I get from here is that the periodic states in quantum computers. So this is the input. But still, why does this work if the amplitudes are all the same, right? Mm. Hmm. What happens if we now do the actual this one? So I'm gonna do it on this one. So I'm just gonna remove this and do that. Hmm. So this is the and what if I replace this with that? That's not what I was expecting. That's not what I was expecting, and that's why probably using different learning material to learn one thing is probably not a good idea always. Um, good. But I'm not giving up on this. So I kind of understand a little bit that concept. I don't know if that's exactly how is this supposed to be done. QFT. How is that your sample? I mean, how is that your encoded sample? Like I don't get that, right? Especially no, what's going on? So if we come back here, so acts on a quantum state and maps it to the quantum state, blah blah blah. Sample qubit. Quantum Fourier transform. So what does a quantum Fourier transform look like for larger n? Yeah, that just applies the thing, and I don't like that explanation because it's just I'm trying to understand a little bit more how to prepare the state at all. Maybe that's just misleading. Um, so what I'm trying to understand is how do you prepare the initial state that's your sample? Because I assume and I understand the sample is, like in this case, for example, that, right? So how do you prepare that? Like, it doesn't make sense to me that those things are encoded in the amplitudes, because you would need to make sure that all the amplitudes fulfill the rule of that if you square them and add them, they are one. So what makes sense to me is that those things are encoded in the phases, right? So you're basically, so what it would make sense, which is at the end of the day maybe what was happening here. Okay, I see this. I was bashing on I was bashing bashing on how this example was built, but really that those things here, I think. So let me just do this here. Was it like I think this was pi. I think this was pi and a half, and I think this was 0.79. Haha. Yeah. So the okay. So the sample is encoded in the but what is U1? Give me a second. What is U1 really? Gates overview. Is it a rotation on the z-axis or what? U1. It's equivalent to the yeah. Okay. It's an RZ. Okay. Equivalent to the rotation in z-axis. No. Here. So it's literally like you could use an RZ. It's the same thing. So you're encoding that into the so to say face. Okay. But I'm curious if that would be a valid thing to do. I guess so. If you have a bigger period, I guess so. I'm not so sure. Okay. Okay, so but this is the way you do it. So you encode your samples. In this case is 0354 minus 0354. Here's kind of complex, and that's actually interesting. How do you? Okay, so that was a bit of a nice journey. I think we really didn't learn. I mean, we learned one thing, which is that actually makes sense. So that's a good step. But I'm gonna do another video on that. I don't want to keep those videos too long. So basically, we're still figuring out how to encode that exactly. So and why does this make any sense? Like why we're like how do we map between like here we've got real numbers and then we are getting into imaginary numbers. And then we'll see how that how the actual QFT works and turns that into the outcome that we want, which are the frequencies of of what's that function made of. Cool. Perfect.